Building software frameworks presents a specific structural paradox. You have to enforce a complex execution sequence along predetermined paths, while simultaneously allowing outside developers to inject their own custom behavior into the microsteps of that sequence. To observe how this tension is resolved in practice, we can look at the lifecycle of saving an object, like a user profile, to a database using an object relational mapper, or ORM. When you tell the application to save that user, it doesn't execute a single database command. It triggers a cascade of background operations, validating the data format, sanitizing the text inputs, and executing the actual SQL query. The framework allows the user class to define its own validation rules, but it doesn't give that subclass the authority to skip steps or alter the overarching sequence. This UML diagram outlines the architectural solution, the template method pattern. As defined by the Gang of Four, this pattern defines the skeleton of an algorithm within an operation, deferring the implementation of specific steps to its subclasses. We are going to deconstruct an ORM database save lifecycle to map the exact anatomy of the template method. Mastering this pattern reveals how complex frameworks use inversion of control to build scalable architecture. At the highest level of our ORM architecture sits the abstract base class, conventionally named record. This split execution flow maps out the save method inside the record class. This acts as our orchestrating template method, listing out the required operations in a sequence: validate, before save, query, and after save. This sequence forms the invariant skeleton of the algorithm. The order of these operations is hard-coded and cannot be bypassed. This structure follows the open-closed principle. The overarching save method is closed to modification. Yet, while the execution order is defined, the actual logic for validation or what to do before saving is intentionally left blank. The template method's primary job is to secure the algorithm's structural integrity, isolating domain logic details. To be useful, the invariant algorithm relies on expansion joints, specific slots engineered into the structure, allowing for controlled flexibility. The first type of expansion joint is the primitive operation. Abstract primitives contain no implementation in the base class. The framework requires the subclass to provide the logic for this step, otherwise the code will not compile. The second type of expansion joint is the hook. Hooks contain an empty or default implementation in the base class. If a subclass ignores them, the algorithm executes safely, but they offer an optional interception point if the subclass needs custom behavior. Now we introduce the right pane, our concrete subclass, the user model. It inherits directly from the record base class. The user class fills in the mandatory validation primitive, supplying a specific domain-level rule, like an email format check. It also opts into the before save hook, supplying a targeted data transformation, like stripping whitespace from a username. Notice that the subclass contains zero routing logic. It dictates what happens, but is stripped of the authority to decide when it happens. When the system needs to persist this data, the application code triggers a save command directly on the user instance. But the execution stack doesn't begin in the user class. It starts in the parent record base class, at the top of the template method. The token moves down to the validate step, jumping across the boundary into the subclass to execute custom email logic. Once finished, control snaps back to the base class, resuming its downward path. It hits the before save hook, jumps right to execute the whitespace trim, and returns left again to trigger the internal database query. This precise, zigzagging execution flow is the technical embodiment of inversion of control. It is governed by a famous architectural maxim known as the Hollywood principle. Don't call us, we'll call you. Normally, a subclass reaches up to call a parent method to share utility. Here, the high-level parent class reaches down to invoke the low-level subclass. Through inversion of control, the framework maintains authority over the lifecycle, relegating the subclass to a provider of micro-details. Scaling this pattern reveals its utility. When we add new entities like posts and comments, they plug custom validations directly into the single record class. This demonstrates the open-closed principle. New behaviors are added without altering the core framework algorithm. But utilizing this pattern comes with an architectural cost, the inheritance tax. Because the template method relies on class inheritance, it consumes a language's single inheritance slot for that object. This results in tight coupling. The domain entity is permanently welded to the framework base class at compile time. This coupling is why modern software engineering often suggests favoring composition over inheritance. The composition alternative is the strategy pattern. Left, the template method uses a solid inheritance arrow, mocked at compile time. Right, the strategy pattern uses an empty socket, allowing components to be hot-swapped at runtime, providing dynamic flexibility and loose coupling. However, in strict framework lifecycles where the algorithmic sequence must remain universally fixed, the template method remains a reliable way to enforce structural consistency.